So we were over here, isn't it? Like we were on this current density topic, uh, how the current density changes and all. We were talking about that, isn't it? So yeah, and how current density affects the magnetic field. We were, we clearly saw that. Okay, so we'll do the first question first. Did you tried it? You tried this question. It is saying that the current density in a wire varies with R as J is equal to J naught R to the power of n. Then find current I in the wire and magnetic field for R less than capital R. So did you try it or what? Basically, I'll show you. Draw the diagram. It says that I have some kind of a wire. Let remain a cylindrical kind of a wire. Word or not? This will be the kind of a wire, and it is saying that it has some radius R. Okay, it has some radius R, and with respect to the radius, the current density is changing. Are you able to get me or not? First of all, it is asking the net current in the wire, that how much is the net current, and second thing, it is asking that find the magnetic field inside it. So basically, to find current or whatever it is, I need to first consider a current element in this or not. I have to consider the first current element, isn't it? Isn't it or not? Like this way. Let's suppose here I am considering. If I want to find the current inside it, I need to consider a current element first of all. Now look over here. Let's suppose this radius of this internal thing. Okay. Consider this to be x. How much is that? X. And this is capital R. Got it? So now look over here. If I want to find current inside it, here current, I know that current varies with respect to current density, isn't it? Are you able to get me? So we definitely now current has a formula I is equal to J J by A or J into J. That is my current density formula. But this is for whole area, isn't it? But to find that how much current lies within this X region, or means over here, let us not consider X here. Let us consider it to be small r. Yes. Ah. So how to find that? How much current is located inside it? See, current density is varying with radius. In this region, I have to find the current. That how much area is there? How much current is there in this area? J is also varying. So you know that for this kind of disk kind of thing, I need to first consider a ring element, isn't it? To do these kind of problems, I taught you earlier also that what you need to consider. Yeah, we see. Basically, look over here. Uh, See, if area is changing, the current will change or not. Little bit of area change, current will also change because density is itself varying. Are you able to get me or not? So our task first of all will be to find, let's suppose I have this kind of system. I consider a ring element, okay, which has inner radius x and breadth how much? Dx. Right or not? This breadth is how much? Dx. Huh? No. I have to find the current in R or not. So first I need to consider some kind of a ring element over here. Got it or not? I need to find that for that ring element what is my smallest current. Then I will integrate over R such that to find. Hmm. If I integrate for capital R, then I'll get the total current in wire. Are you able to get me or not? So look over here. For this ring element, as you know that it will have a small area. So a small area for the ring element is simply going to be how much? It is equal to, sir, as I know, length into breadth. Length is 2 pi r and breadth is dx. So area of the, yes. So ring element area is 2 pi x dx. Are you able to get me or not? Now here it is r to the power of n. So current inside, let's suppose if I want to define current, current equation will be integral J is what? J naught r to the power of n, so it will become x to the power of n 2 pi x dx. So this is equal to 2 pi j naught outside integral x to the power of n plus 1 dx. Are you able to get me or not? Now, if I want the total current, therefore total current in wire is integral 0 to capital R. Sorry. Y. No. That is integration over here. Inside the this is n x to the power of n. This is x to the power of n. So that it will become x to the power of n plus 1 or not. So total current in wire is 2 pi z naught, uh, 0 to capital R x to the power of n plus 1 dx. So this becomes 2 pi z naught, got it or not? 2 pi z naught, x to the power of n plus 1 divided by n plus 1, 0 to capital R, isn't it? So this is 2 pi z naught. What it will become? R to the power of n plus 2 divided by n plus 2. And if it is 0, then it all the terms are 0. Are you able to get me or not? Is it clear? So that is the total current in wire, isn't it? In second question, it is asking find the magnetic field inside this, inside over here, this point, isn't it? So how to do it? Simply first find the current inside R less than capital R. It is equal to same equation 2 pi z naught R to the, only the equation will change, R to the power of, sorry, a small r to the power of n plus 2 divided by n plus 2. And then I can apply the formula, na? That integral closed loop B dot dl mu naught I enclosed, which is 2 pi n naught, sorry, 2 pi z naught r to the power of n plus 2 divided by n plus 2. So B dot dl, B is how much I have to calculate, dl is 2 pi r mu naught 2 pi j naught r to the power of n plus 2 divided by n plus 2 pi cancel, and this is 1 minus, so p is equal to mu naught j naught r to the power of n plus 1 Let me write it perfectly. Can you get it or not?
Yeah.
Mu naught J naught R to the power of n plus 1 divided by n plus 2. That's your formula. Okay.
Yes.
Is it clear?
Yes.
So this is what you need to do. Every time whenever you get a question, try to solve it. Okay. Can I move ahead?
Yes.
Any doubt? Okay. Okay. Move on to next. It's saying that there is a cylindrical long cavity. Uh-huh. What? What?
2D diagram.
Okay. So what is happening with 2D diagram?
Will that be helpful?
Yeah. You can draw 2D diagram. So see, this is my cylinder, isn't it?
Yes.
And inside it, I created some kind of a hollow cylinder. I'm considering kind of a cavity. I'm considering, isn't it? Like this one.
Yes.
Okay. So see,
Yes.
this is my axis of the cylinder. So it's saying that in a cylindrical long, a cylindrical long cavity r less than a small r means the radius of the cavity is small r, isn't it?
Yeah. At least less than 2.
Yeah, a small r, and this is capital R.
Yes.
Got it?
Correct.
Some kind of such cavity is maintained, and cavity is parallel to the axis of cylinder. Prove that the magnetic field inside the cavity. Okay, so I want to prove the magnetic field inside the cavity
Is
that
correct.
needs to be uniform. Means such kind of magnetic field should be present. Means due to the current in the long wire, there is a magnetic field inside the cavity. Are you able to get me or not?
Yes.
And that needs to be uniform. That it's what needs to prove. Are you able to get me?
Yes.
So how to do it?
We will construct the 2D diagram.
Should we construct a 2D diagram? Yes, we need to construct a. See, first, just we need to construct the upper part of the cylinder. See, this is my cylinder, and in that there is a hollow cavity, isn't it?
Yes.
Void or not?
Correct.
So I'll draw like this way. This is like this kind of a situation,
Yeah.
isn't it? So now here you can see. Let us consider that its center is O. Center of bigger, you can say that whole cylinder is O, and then the center of this will be, let us consider to be A. How much I'm considering?
Yes. A.
A. Are you able to get me or not?
Yes.
And I want to find at some point P my magnetic field. Is that clear or not?
Inside the cavity. Yes.
Yeah. So how I can imagine? I'll consider.
You can consider that.
Uh, but what?
Triangle. Can we draw a triangle?
Why to? Yes, that is also correct idea. We'll draw a triangle. But before drawing a triangle, we can imagine like this kind of a situation or not. That first,
Is it the center?
yeah, first considering that this has plus sigma. current density, while this has minus j current density. Just like electric field we proved now, plus sigma j, and this is minus j. Are you able to get me or not?
Yes.
Is that clear? Or you can even consider, let's suppose this is plus j, okay, and let's suppose if you are in addition form, if you do not want to add, since current is a scalar quantity, you can directly put minus. Are you able to get me? Clear? Yeah. So this is looking like uh, center O, and here is my point P. I want to find the magnetic field. Here is my center A, and here is my point P, where I want to find the magnetic field. Are you able to get me or not? Now, if this is some kind of, let us consider that this is a whole big surface. So current in existing over here is I1, and here the current existing is I2, because this is a small region, isn't it? So magnetic field at point P, therefore magnetic field at point P vector can be imagined as magnetic field due to on magnetic field at P due to O, means this line, this line, heard or not, minus magnetic field due to at P due to A. Is that clear? Ah. So earlier when I was discussing Biot-Savart's law, I gave you the formula of Biot-Savart's law with the help of current density, isn't it? Do you remember that? Wait, let me check whether I have given or not. Okay, I didn't have given. I didn't have given. A straight wire, I directly derived it. Okay, okay. No problem. I'll write over here. Okay, see, Biot-Savart's law formula is what? dV is equal to mu naught I dl vector cross r vector divided by r cube, isn't it? That's my which formula? Yeah, this is a vector formula, isn't it? So question arises that how to write this whole formula in terms of current density, isn't it? Because actually you should be, yeah, tell me. See, actually what you will be aware of is the current density, not some kind of this kind of formula. Are you able to get me or not? So question arises that how to write in terms of current density, isn't it? Now you only think current density includes the area, isn't it? So if I write for a solid cylinder, when I'm going to write for, say, here we have a solid cylinder now. So see, when we write all those magnetic fields, this is what, if it is less than r or something like that, or anywhere, so it is mu naught I r by 2 pi r square, isn't it? So inside it you see B inside, not, I'm not talking about outside. Outside will take all the current. But inside you see, here it can be written as mu naught by 2 r I by pi r square or not. I by pi r square is what? Current density, isn't it? So another formula over here, that B inside in terms of current density can be also written as mu naught by 2 J vector cross R vector, isn't it? For R less than R. Are you able to get me or not? Correct? So we can define this. Yeah. Sorry. So we can define the magnetic field inside the solid cylinder. It has a formula. B vector is equal to mu naught by 2 J vector cross R vector. Is that clear? So here it is, P point is inside point. If I talk about R vector, then R vector is OP vector or not? Yeah, so it will be mu naught J vector cross OP vector divided by 2. Are you able to get me? Write it fast, then I'll move ahead. Then this is mu naught by 2 J vector cross AP vector, because this is also AP. Are you able to get me? Then what we can write as equation? Can we write that B at P is mu naught by 2? I can take J vector common, J vector cross OP vector minus AP vector. So I can write it as plus PA, plus PA vector or not. But what is PA vector? PA OP vector plus PA vector. If you look over here, it will follow triangle's right hand rule, and it is equal to, as we can say, that OP vector plus PA vector is equal to simple OA vector. Are you able to get me or not? So therefore, I'll get magnetic field at point P as mu naught by 2 J vector cross A vector, which is uniform. Are you able to get me or not? And let's suppose if the distance between the center is A, then the magnetic field simply at any point inside the cavity is simply mu naught Ja by 2. Can you hear me? Yeah. Is it clear? Okay. Are you able to get me or not? Yeah. Write it fast. Hello. Can you hear me now? Okay. Can I move ahead? Okay. Okay. Let us write one more question. Okay. So it's saying that there is a coaxial cable. One minute. Okay. Question is very simple. A coaxial cable is made of a thin straight wire. is made up of a thin straight wire and a thin hollow cylinder.
Yes.
Okay. Find magnetic field, point B at a distance find magnetic field at a distance r when first case r is greater than capital R, second case r is less than capital R. And see, I'll show you the direction of current. Current is going in this. See, this is a, what it is saying, a coaxial cable is made up of thin straight wires. Got it or not? These are my thin straight wires and the thin hollow cylinder. Got it?
Yes.
So remember, this cross means thin straight wires. Are you able to get me or not?
Okay.
And this is some kind of current I is flowing through that. And this is radius R. And in this also cylinder, hollow cylinder, there is a current I going. Got it or not?
Yes.
Then find the magnetic field.
Is that what of the cylinder that's
Yes, yes. Okay, one thing is damn sure if I consider for R less than R, what is the answer? 0 or not?
yeah,
Because it is a hollow cylinder, not a solid cylinder, isn't it?
yeah, I understand what you mean correct.
Yeah, for this reason, for this a small r, 1 minute, for this a small r, the if I apply Ampere circuital law, so second one, integral B dot dl is mu naught I enclosed. So I enclosed is 0, so mu naught into 0. This means B inside is how much? 0.
Yes.
Correct now.
Yeah.
And when I consider a out point, let's suppose this is I'm considering a external point for r greater than capital R. Okay, so if I apply integral B dot dl, then mu naught I enclosed I have to consider. But see, on hollow a region, the current will never be present inside it. It will be present on the surface also, although it is drawn over here. Are you able to get me or not? So that means the net current present on the surface is how much? Total current is I. Right or not?
Yes.
So therefore, B into 2 pi R is equal to mu naught I. B is equal to mu naught I by 2 pi R. Many people will think that I will add it with I and it will become 2I. It's not possible. Charges cannot increase. Are you able to get me?
Yes.
Okay.
Yeah.
Can I move ahead?
Yes. Okay. Yes.
right? Okay. Now comes an outstanding question, last outstanding question based on the Ampere circuital law. Last but not the least, as we say. Okay. So basically, sorry. Yes. Got it. Can you see the picture? 1 minute. Let me draw it like this. So this is a this is some kind of a pipe. Word or not? Yes. Is it visible like a pipe or not? Yes. Yeah. So it's a pipe, and on this pipe, some kind of a current is flowing. Let's suppose the current which is flowing is I. It's a half pipe. Word or not? Question is, find the magnetic field. Find the magnetic field on axis of find the magnetic field on the axis of very long current carrying half pipe. Very long current carrying half pipe. Do it. Do it fast. Can I do it?
Is the half pipe solid state or hollow?
It's a half pipe. Pipe means what?
Yes,
Hollow cylinder.
solid.
Yeah, pipe means only hollow cylinder, isn't it?
Okay. Will it be mu naught I by 4 pi?
Mu naught.
I by 4 pi.
Mu naught I by 4 pi I. No.
R, R.
No. Think. You have to think.
How many axes? Any 0 or 1?
Okay, should I help? See, as I'm considering that it is a very long wire, the first task is, see, uh, you should understand that current is spreaded on this whole wire, isn't it?
Yeah.
Like this way, means totally spreaded here and there, here and there, here and there, everywhere, isn't it? But
Yes.
I want to find some magnetic field at the axis, means at the center. So see, I have to consider for that. I'll be required to consider one what element, some kind of a element I need to consider first of all. That sir, definitely I need to consider some element such that with respect to this strip element, I can find the magnetic field at the center. Are you able to get me or not? And it
Okay.
is very see,
Axis.
yeah. So it has a very small angle d theta. Are you able to get me or not?
Yes.
And with respect to horizontal, let me write perfectly. This angle is what? D theta. Word or not? And with respect
Yeah.
to horizontal, let's suppose this is making some kind of angle theta. Word or not?
Yeah.
Then at least if I can integrate till half, then or integrate till over here from theta is equal to 0 to pi, then I will cover the whole half pi for now.
Yes, yes.
So look over here. Basically, you can see that see, this is some kind of a semi circular strip only.
Yes.
Got it?
Yeah.
Wait. Yeah. Nice idea. So can you see that now? That
Yeah, yeah.
over here,
Yeah, yeah.
if I consider this is my center, and as I consider a small element over here, I'm considering which is of d theta, and it's making some angle theta with respect to horizontal. Are you able to get me or not? Is that clear? And the current is passing. Current is passing in what way? Current is going like away from the this region or not. So current is like a dot for it outside of the plane. Right or not? Is that clear? So now look over here. When I will draw the magnetic field, current is coming outside. It will be in this plane. So let's suppose the net magnetic field for this, it will be in perpendicular direction or not. So this is my magnetic field. Are you able to get me or not? For this current element. So look over here. If it is theta, then this angle is how much? 90 minus theta. And this is radius r. So then the current element has a length how much? RB theta. So look over here. If I write the magnetic field formula, magnetic field is mu naught by 2 pi r. It is a semicircle. So 2 pi r into di, isn't it? That will be the equation because I'm considering it to r d theta only. Are you able to get me? Yeah. So this is what? Mu naught I, mu naught by 2 pi r. What is di? Total current. Total current is I spreaded on, how to say, pi r total area pi r square, isn't it? Pi r square by 2, I think so. Or pi r square. Yeah, so pi r square by 2. Yeah, so it is 2I by pi r square, isn't it? Correct now? I'm thinking correct now. Yes. And into r d theta. Are you able to get me? No, but wait. I think defining with respect to area will not be good because current is not present on area. 1 minute. This current is only located on the line segment or not. So I need to define the linear current density. Which kind of current density? Linear current density. So I by pi r, that's my length. And how much length it is present in r d theta? So I by pi r into r d theta. Are you able to get me or not? So dv is equal to mu naught I by 2 pi r square r d theta. Are you able to get me? Now see, ultimately you can see that this magnetic field has two components, isn't it? One sine theta, one cos theta. This is, so look over here. This is dB cos theta because this is going to be theta and this is dB sine theta. R cancel na. This R and this R will get cancelled or not. Okay. So look over here. There are two components, sine theta and cos theta. So net magnetic field along x is integral dB sine theta. So integral dV is mu naught I by 2 pi r square, 2 pi r square r sine theta d theta. And this sine theta varies from 0 to pi degrees or not. So integrate it. How much I'll get? Sine theta integration is cos theta. So bx is equal to mu naught I by 2 pi square r cos pi minus cos 0. So this is minus 1 minus 1. How much is that? Minus 2, isn't it? But if I include the magnitude only, means this dB will be present opposite actually. Mhm. So mu naught I by pi square r, if we considering the magnitude. Isn't it? Are you able to get me? Next thing I want to find due to which reason? I want to find due to by. So by is dv cos theta, and cos theta is integration sin theta or not. But sin theta will be definitely 0 for 0 and pi or not. So answer is already 0. By is how much? 0 means this component magnetic field does not exist. The net magnetic field component is only along x axis, which is opposite towards this side. Means it is present towards along this side. Are you able to get me or not? Is that clear? Right. Totally clear? So, so what I'm planning is now solenoid left, toroid left. Okay, solenoid, toroid, infinitely long sheet, moving charge, rotating hollow cylinder, moving charge sheet, Gauss law magnetism, magnetic force on moving charge, deviation, then charge particle, deviation. EV component, cyclotron. Okay, so this is a phase of almost, I'll tell you. So what is my plan is that some parts of EMI, electromagnetic induction, okay. Hello, can you listen me? So some parts of electromagnetic induction I will do with this chapter only, word or not. Okay, some parts means which are there because ultimately those things are required over here only, word or not. So remember that this is a total notes of 127 pages in my note copy, and we have only completed till 40 pages right now. Still 80 pages are left. Okay, so we have to complete it fast. Within 10 days, we'll try to complete as soon as possible. Okay, and then we will move ahead. Now, let us give the heading magnetic field due to a solenoid. Today evening, there is a 2-hour class, okay, of center of mass and rotational motion, okay, because I'll take only 1 hour class right now as I have to end up. They have shared me the timetable right now. This guys, magnetic field of solenoid, right or not? Now see, right now I'll write the formula, but later on I'll make you understand how to use it and what is the main discussion regarding that. Okay, so first thing you should remember that a solenoid is based on a circular kind ring material. Okay, a circular kind of ring material. Are you able to get me or not? This is like this. Word or not? Now, and there is a binding on top of it. Everywhere on each segment there is a binding. I'll draw it. Give 1 minute. Mm-hmm. 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 Okay, so see how the binding is done. They will make flow of some current, and then it goes like down this way. Got it or not? Can you see? Okay. So this is my some current passing through it. This is my current that will come out of it. Are you able to get me or not? And let's suppose this cylindrical thing is of length L. Then magnetic field inside it. Basically, the magnetic field exists inside it, not outside. That's a very big phenomenon. Got it or not? And that magnetic field is given by formula mu naught n. N is the total number of okay. So mu naught n I by length L, where n is the total number of turns and L is equal to length of the solenoid. Now we define a new number, a new kind of a n, which is total number of turns per unit length. Okay, so that is this makes our net magnetic field equation. This is makes B is equal to mu naught n I or mu naught n by ni by L. That's the formula for solenoid. Are you able to get me or not? Clear? Is that clear? So we'll keep it over here. There is toroid and all those kind of terms, and we'll get through it, solenoid, toroid, and all after some time. Got it? And we'll also understand how the current comes in this, how the picturization of magnetic field is here, and how it is appearing. Got it or not? All these things we will discuss. Is that clear? Okay. So I'll share you the notes today. This is already 46 pages done. Okay, so I'll show you the note. I'll share you the notes and then we'll move ahead. Okay, चलो तब तक के लिए टाटा बाय बाय. Okay, let's meet in the evening 10 p.m. exact. Okay.